Hi there. All right, so we're going to look today at inverse functions. This chapter is actually more about exponential and logarithmic functions, and those happen to be inverse functions. Just like a squaring function and a square root function are inverses of one another, so are exponentials and logs. So we sort of introduced that idea of how inverse functions work before we get started into chapter 4. We have something we call one-to-one functions. And for a one-to-one function, each x value corresponds to one y value. You're probably familiar with that concept. That's what defines a function, really. But a one-to-one function also works the other way, where each y value corresponds to one x value. So it has to work both directions for it to be one-to-one. So looking at these, we just kind of go back and do this mapping thing. First of all, you're looking at a mapping. Each one of these x values, looking at this first green one here, each one of those x values here corresponds to exactly one y value. But it also works backwards. Each one of these corresponds to exactly one. So trying to decide, is this one-to-one or not? Yes, that would be a prime example of something that's one-to-one. All right, let's make it a little fancier here. Let's look at this one. All right, so this, you can see there's only one line coming out of each number. Now they start mixing it up a little bit and they're crisscrossing. That doesn't really matter. As long as you have one line coming out of each and one line coming out of each of these. So another example of one-to-one. Looking at our next one, this peach colored one, again, one line coming out of each, meaning each one of those gets mapped to exactly one value. But over here, it wouldn't work the other direction. This -3 right here has two values going the other direction. So you can't have two of them coming out of the same value because that means that -3 is being mapped back to -2 and back to -4. That is not considered one-to-one. All right, you do that last one. What do you think? All right, hopefully you said, nope, not going to work because right here, this 12 has a couple values coming into it. So does the 6. So not one-to-one. Now, we don't really use mapping like that. You don't usually see it like that. You might see ordered pairs more likely, or a table of values. But also, we want to be able to look at something that is an equation. And can you determine if that would be considered one-to-one? The way this might work, or how you think through it, is that if you're going to put a value in for x right here, if you put some value, is there any way that you would end up with two different values for your y value on that? And no, you're just going to plug this in and whatever you get back is what you get back. But it also has to work the other direction. If you had a value over here, is there more than one way to get to that value? And looking at this, it's just linear. There's nothing fancy going on here. This would be considered a one-to-one. But let's look at B. Here's an example of something where if I put a number in for x right here, I might put in a 3. I get a 9 minus 4, that's a 5. There's no way to get a different number. I'm not going to get multiple answers over here. But if you think about it the other way, like let's let this be, I was going to do a 0, but I don't know that I love using 0 as an example. So let's do 5. Let's let it be 5. Okay, so if I put a 5 here, the question is there more than one way to end up getting a 5 there? Well, I could put a 3 right here. 3 squared is 9. 9 minus 4, that's 5. But I also could put in a -3 right there. A -3 squared is 9. Minus 4 is still 5. So if I have two different ways of making that happen, it's not going to work. It's ultimately, if you were to see your table, it'd be you get 3, you'd get a 5. If you put in -3, you'd get a 5. So on a table, you wouldn't want that. So that would be considered not one-to-one. Okay, last one, a square root function. If I put some number in for x, whatever that might be, let's say it's a 5. 5 minus 4 is 1. Square root of 1 is just 1. I'm not going to get multiple answers back. But the question, I guess, is there other ways to end up getting a 1 here? Yeah, I can get a 1 by putting in 5. Is there any other way? And on a square root function, no, there's not going to be. This is actually going to be 1 to 1. Now, it's kind of tricky sometimes to just imagine that or think through every possibility on equations. So we have other options. If you'll recall, when we try to determine if something is a function, we use a vertical line test to determine that. If you can pass a vertical line through the graph and it only touches once, then we know that it is a function. To determine if its inverse function, if its inverse is a function, then we use that horizontal line test. If you run a horizontal line test through the graph and it only hits your graph one time, then the inverse is going to be a function. So for something to be 1 to 1, we really want it to be a function and we want its inverse to be a function. So it has to pass both line tests for it to be considered a 1 to 1. And that's maybe the easiest way to think about some of these. So looking at 3, does it pass a vertical line test? Yes. Does it pass a horizontal line test? No, it does not. So this is not considered 1 to 1 because it doesn't pass both tests. Looking at the next one, we have this nice cubic. It passes a vertical line test, so it's a function. It passes a horizontal line test, so its inverse is a function, and thus it is considered 1 to 1. So if on that previous slide when we were doing equations, if you're not 100% sure looking at the equation, consider the graph of it. We had that one that was a quadratic. It looked like this. And since a quadratic does not pass a horizontal line test, it's not going to end up being 1 to 1. But then that third example that was there was a square root function, and it passes both a vertical and a horizontal, so it would work. Now, if you're going to have a function and it's an inverse function, and its inverse is also a function, your notation for that is going to look like this. It's an f with a little -1 here of x. So if the inverse is a function, you can use that notation there to show that. All right, so here we go. So let's complete the tables for the function and then its inverse. So here's my f of x function. I'm going to put -1 in. I'm just going to do quick mental math here. I would get a 2 back. If I put in a 0, I'd get a 4. Put in a 1, I'd get a 6. Put in a 2, I get 8. Okay, that's a nice function. I'm getting different values every time. And I've already acknowledged, well, I can just look at it, say it's a line. So I know it's going to pass both vertical and horizontal line tests. It will be 1 to 1. So they've already done kind of some work for me, and they're telling me, here's the inverse function for that. All right, so let's finish the table out for this. If you put a 2 in for x right here, 2 minus 4, that's a -2. You get -1 when you divide it by 2. Let's put in a 4. 4 minus 4 is 0. 0 over 2 is 0. 6 minus 4, that's a 2. 2 over 2 is 1. 8 minus 4, that's 4. 4 over 2 is 2. All right, now really filling out a table isn't really what I'm trying to show you here. What I want you to catch is comparing the two tables that we have. This is the result of the first scenario. And look at what happens when you did the inverse. This -1, 2 turns into a 2, -1. 0, 4 is now 4, 0, and all the way through. So inverse functions, their x's and y's swap, and they'll flip-flop. So you can use that concept of knowing that inverse functions will flip-flop their x's and y's. You can use that to graph any kind of a function. So here I have one. It's not any function we necessarily know, but you can see that it passes both a vertical and a horizontal line. So I'm going to graph the inverse of it using that idea that the x's and y's will flip-flop. So I have this ordered pair right here. That is a -4, -2. So my -4, -2 is going to turn into a -2, -4. And I just go plot that point. So -2, -4 is right here. Let's try it again. This point right here is -2, or +3. If I flip-flop it, it's now a 3, -2. Let's go plot it. Over 3, down 2, it's now here. And so these two would connect. And then the last one, over 2 up 4, is going to turn into an over 4 up 2. So over 4 up 2, boom, and we connect. And this is the inverse of it. Now, there should be a little bit of a pattern here that you notice. Because you're flip-flopping the x's and y's, they sort of have this reflection over each other right through this line here. This point reflected over to here, this one reflected over to here, and this one reflected to here over this line. We're going to talk a little bit more about that later. Now, inverses have a lot of features, and we're trying to kind of hit on all the different things that might happen, or do happen, I should say, with inverses. And here's another one. It kind of ties in what we've done previously in this course, but it says F will be 1 to 1 if G is the inverse of F. Okay, let me restate that. Sorry. Let F be a 1 to 1 function. Okay, so F is 1 to 1. So that means G is the inverse function of F if these two things will hold true. If you do these composite functions, F of G of X should end up equaling X for anything that you plug in for X. But also G of F of X should end up reducing down to X. In other words, remember when you do the composite function, you plug one function into the other. So in this example, I'm going to put G in for F. And what happens is everything kind of starts to cancel out until all that is left is an X. But it also needs to work the other direction. When you put F into G, does everything sort of cancel out till all you have left is X? I'll show you what I mean. To verify, the functions are inverses. So they're kind of telling you already these are going to be inverses. To verify it would mean to prove it to me, showing me that F of G of X and G of F of X both equal X. Now, I did not give us very much room here, so I apologize. We have to write little on this. So the first thing I'm going to do is I'm going to do F of G of X. So it looks like this, F of G of X. That means take G, plug it into F function. All right, now I'm going to undo that drawing because that's really going to clutter up our work here. So I'm going to take G and put it in for the F. So it's going to look like this. 5 over, and instead of X, I'm going to put that entire G function. Kind of messy. That's all right. Just keep it neat as you can. All right, now the goal here would be to then sort of simplify and see what can happen. Well, I can see right off that this +2 and -2, those are going to cancel out. So then what I have left is a 5 over 5 over X. I'm going to pop that up and multiply by the reciprocal, multiply by X over 5. Well, a 5 times an X over 5, this 5 and this 5 would cancel. And then all I have left is this X. All right, it worked that direction. Now we've got to go the other way. So now I have to do G of F of X. So now I'm going to start over. I'm going to take the F and put it into the G function. So G looks like this, 5 over, and instead of that X, I put in the F function. And then I'm going to add 2. All right, this looks a little bit messy, but I'm just going to kind of plug along and do my algebra that I know. This first 5 right here, sometimes I think it helps if you write these as a fraction, because that's a 5 over 1, and I'm going to pop this up and multiply by its reciprocal. So when I multiply by the reciprocal, I'm going to change colors on us because it's getting a little bit messy. I'm going to have an X minus 2 over 5. Now, when you do that, this 5 and this 5 will cancel. And what I have left, I'm going to rewrite here. So then what I'm going to have left is just this X minus 2 right here. That's going to still be sitting there. These 5s are gone. but then I still have this plus 2 out at the right. So it's going to be an x minus 2 and then a plus 2 out at the right. And you can see that, oh, minus 2 plus 2 cancel, and I'm down to just it equals x. That's what I wanted to have happen. All right, so I did one, practicing that composite function going both directions. I want you to pause the video, and I want you to see if the next one works out the same way. You have to work it through f of g and then g of f. Try it both ways. Pause the video for a moment. Okay, so I worked it out. Hopefully you did too. Looks like it worked out just fine. That means those functions are inverses of one another, and it's 1-to-1. Okay, so we're going to take a minute. We're going to look at some graphs of inverses. We had done one earlier, but we're going to look a little deeper into it. It says first, verify whether the functions are inverses. Then graph both equations. All right, so I'm going to do f of g of x. That means take g and put it into f. All right, so I'm going to have a 2, but instead of an x, I'm going to have a 1/2 x plus 2 that I plug in, and then it's a minus 4. Okay, sometimes you can kind of look at them and say, oh, that makes sense that the times 2 divide by 2 should cancel each other out, and that's how everything reduces down to x. But this minus 4 looks a little suspicious here because I don't have a 4 that's going to cancel out with. But if I just do the process, you'll see that you end up right here, 2 times 1/2 x, and then 2 times 2. So what I end up with here is just an x plus 4, and then the minus 4. So it does actually, that 4 does pan out to where it'll end up canceling. All right, let's see what happens if you go the other direction. I'm going to do g of f of x, which means take the f and put it into the g. So I got a 1/2, and instead of x, I get the 2x minus 4, and then a plus 2 out to the side. All right, go ahead and distribute. 1/2 times 2x is just an x. Half of 4 is a 2. And once again, you can see that the 2's are going to cancel out, and we get just an equals x. All right, so we verified it there. So now I truly know these are inverses of one another. We've got a 1-to-1 situation. Now what I want to do is I want to graph them. So the first one is a 2x minus 4. Y-intercept of -4, slope of 2. Right? Purposely making this plenty long, so you'll notice something here in a minute. Okay, my other line is has a y-intercept at 2, and it has a slope of 1/2. Rise 1, run 2. Rise 1, run 2. Okay, going this way. Let's go back this way. Okay. Can you hear that? I'm in a hotel room, and the police sirens are going. Okay. All right. So if you'll notice this, like the last one, these two lines actually reflect over this line right here. They would reflect on top of each other. That actually is going to happen every time. If you truly have 1-to-1 functions, they're inverses of one another, then they will always reflect over the y equals x line. That ties into that whole idea of the x's and y's swapping. That's why it will reflect over this line. So just another feature that can help you determine or find or verify, confirm, whatever you're doing with your inverse functions. They will always reflect over this line. Now, each time here, I've been giving you the inverse and just having you verify that it's that. But, if we already know the inverse, there's probably a good chance that we're pretty sure it is. But what if I didn't give you the inverse? How do you go about finding it? All right, so to determine if the function has an inverse, now, if it has an inverse, if it doesn't have an inverse, then you're going to stop and you don't keep plugging along. So remember, for it to have an inverse, it's going to have to pass the horizontal line test. If it is a function, it'll pass a vertical, but for it to have an inverse that's a function, it passes a horizontal line test. If your graph does not pass a horizontal line test, then stop. You're not going to go find in one. So let's say that it works out. Yep, it does. So let's go find it. So what you do is you're going to take this f of x, you're going to replace it with a y, so that you're thinking, oh, you got x's and y's. Then you're going to swap the x and y. And then you're going to rearrange it, go resolve it for the y. And then you have found the inverse and you replace that y with this better notation to indicate that it is the inverse. This is sort of your to-do list right here. Let's give it a shot on the next slide. I have several examples here, 4 different examples. So let's start with A. All right, looking at this, it's kind of a fancy equation, but not really. It's just linear. It just looks messy because it's got the fraction stuff going on. But your x is just a linear function. And lines pass both vertical and horizontal line tests. So I'm going to be good to go to find the inverse. First thing I do is switch the x and the y. Well, change this f of x to a y. And then I'm going to switch the x and y. So it's going to be an x equals 5 minus 3y over 2. And now you want to go rearrange it and get that y isolated, so it's a y equals. So I'm going to take it times 2 on both sides to get rid of the fraction. I'm going to subtract the 5 and divide by the negative 3. Okay, so what I have now is the inverse function. So I'm going to final answer. I'm going to rewrite it with that nice inverse notation. My inverse function is 2x minus 5 divided by negative 3. Now, just to notice some things, up here I was multiplying by a negative 3. Down here I'm dividing by a negative 3. Up here I'm dividing by 2. Down here I'm multiplying by 2. It feels like I do have some inverse things going on. But don't get too caught up in that because sometimes it gets a little bit buried and you don't notice everything. Okay, next one, B. You have a cube root function. All right, if you'll remember, a cube root and a cubic, those would be inverse operations, and a cubic sometimes will pass a vertical line test, sometimes will not. I'm sorry, a horizontal line test. Depends on if it's just your standard or if it gets fancy and does that to you. All right, so looking at this one, I think it's going to be my standard. I think I'm going to be okay. So I'm going to go ahead and imagine that this right here is just a y, and I'm going to switch the x's and y's. So it's going to be x equals cube root of y plus 1. And now I'm going to rearrange it, isolate the y. So to do that, I'll want to cube both sides first. So it's going to be x cubed, and this cube will go away. And then I'm going to subtract the 1. All right, not as much happening here. Oops. All right, final step is to go ahead and write it in that inverse function notation. Oh, you know what? I'm going to change this because it was a g function, not an f function. It's not always f. So this one's g. So I would write the inverse of g is equal to x cubed minus 1. Okay, I'm going to let you try C. Well, never mind. I'm not going to let you try C because look at C and D. They're the same thing. Okay, but if you look at C, it says that it's x squared minus 2. I know that that's a parabola that's gone down 2. The problem is that I know that a parabola that has gone down 2 does not pass a horizontal line test. So remember, if it's not 1-to-1, if it's not going to pass a horizontal and vertical, then stop. There is not an inverse for this. And so I would write not possible. But then, of course, mathematicians don't like to be told they can't do something. So they tweak it and make at work, sort of. It's sort of like how we do imaginary numbers. It's how we fix problems. We just make up stuff. All right. So here, this one, it's still a parabola, but what I've done is I've tweaked it. I'm only looking at the parabola when x is greater than 0. So that graph that I just gave you, I'm only looking at this portion of it. Now, does it pass a vertical and horizontal line test? Yes, it does. So that's how we can tweak something so that we can go ahead and find the inverse. But we'll have to consider this as we write our inverse, that we did limit our domain on this. So we'll have to look at that on our end result also. Okay, so real quick, I'm going to call this a y, and I'm going to switch the x and y. Go resolve for y. Now right here, I'm going to square root both sides. Now I'm used to doing square root both sides should be a plus or a minus. So I would have here final answer, sort of ish. That's a q function. So the inverse of q is a plus or minus square root of x plus 2. All right, now that's what I think the inverse should be. But I've got to consider that, well, I kind of tweaked this originally. Let's look and see what happens. I know that a square root function is a sideways parabola. The plus 2 inside here is making it go left 2. So it's going to look like this. But the plus or minus gets me the bottom half also. And that's problematic because I know that this won't pass a vertical line test. So that plus or minus, I don't really care for. And so what I would do on this is to make this actually work is I wouldn't include the plus or minus part. I would just do the plus part, then it would work out. Now here's how I also know that this would be the shape. This is the part that I would want, is that if you look at my original graph over here, I'm going to make it red. This graph right here would be right here. Do you see how that one and this one reflect nicely over this y equals x line? All right, so I'm going to change this. This is not really what my inverse is going to be. I'm going to rewrite it here. It's actually going to be this without the plus or minus. So just this right here. And then that way, I've taken care of the fact that I edited the domain here. And in the end, then I've edited the result as well by not including the minus on that. Okay, so as you approach your homework here, you have to kind of understand all these different relationships that we've talked about, from swapping the x's and y's to the graphs reflecting over that y equals x line and the whole vertical and horizontal line test. And you really have to tie together all those concepts and know what you've already learned in this course as far as considering what your parent graphs and then their transformations. Can you envision or give yourself a little sketch of what that graph looks like? And then know, yes, that's going to have an inverse, or no, that's not. For example, do you know that a quadratic, well, that's a parabola. That is not going to pass a horizontal line test. So it's not going to have an inverse unless I alter the domain to allow for that to happen. Okay, how about a rational graph? That's this one right here that we've spent a lot of time with. All right, that's going to pass a horizontal and a vertical line test. It's going to be okay. A square root is okay, as long as you don't do the plus or minus where you get the bottom half of it. Don't do that. A cube root actually looks like this. As long as it doesn't get too fancy, it's going to be okay as well. So just going back, maybe think absolute values or whatever functions that we've already graphed. Will they pass a horizontal and vertical line test? All right, so again, B, you're considering all the stuff. You're the swapping X's and Y's. The horizontal and vertical line tests. The reflecting over the y equals x line. So many different relationships here that we've talked about. But among all of those, you should be okay on your homework. Good luck.